The next speaker is Vandi Verma, the Chief Engineer at NASA-JPL Rover Robotics Operations. And Vandi will be talking about driving curiosity and perseverance.
Yeah, thank you for the introduction. So today I was going to talk about Mars 2020 robotic operations and touch upon some of the adventures of operating the first rover and helicopter on Mars. So starting out, I was just going to cover what Perseverance robotic operations covers. And so it involves all of the mobility and navigation. So that's all the driving that we do to get to the different science locations and everything that's done with the robotic arm. So the main purpose of the robotic arm and why we send a rover is because we want to take measurements in situ, really close proximity observations on the surface. And we deploy the tools and instruments at the end of the robotic arm. There's a turret, a 45-kilogram turret, which really carries a lot of the payload. And we can deploy instruments within centimeters of the surface. But it also does a lot of other things like docking with the body of the rover to exchange the bits, which you're seeing in the bottom right image, because inside the rover, the bit carousel that it's docking with has an entire robotic system inside the rover that it is able to put the tubes in and interact with, and also doing things like taking the self-portrait. And the sampling, which I was touching upon, covers the aspects which are, of course, the coring, because the purpose of the mission is to cache sample cores in a large way, and to also, abrade rocks, because Mars is a dusty place, and a lot of the instruments are very sensitive, and we want to blow away the dust from this. So we abrade it, and we also have a gas dust removal tool that can blow away dust from it and study them. And so that's a lot of the sampling system. And then there's the helicopter, which is the Mars helicopter, of course. INGENUITY is also part of the robotic operations. So where are Perseverance and INGENUITY right now? And this image here is an orbital image showing the path of the rover and helicopter. So we've driven 2,600 kilometers, and the white path is Perseverance's path. The blue dot shows where Perseverance is right now. And this is from Sol 210, and we were just in Mars conjunction. And so, today is Sol 233, and we're still at that same location, and we'll be starting operations again tomorrow. And the robotic arm and sampling, we've sent over 20,000 commands. And at all of the locations where you see the stops, the white dots, we will often deploy the robotic arm and take images with the imager at the end of the robotic arm, the Watson camera, or pixel Sherlock observations. And the two locations where we have cached samples are shown in red. So the first one at the bottom, the southernmost one, is Rubion, where we took an atmospheric sample, and the one at CITADEL is the Rochette location, where we cached 2 rock sample cores. And we've done 13 flights, which have covered over 2,300 meters. And the green path is showing INGENUITY's path. And the orange dot, keeping with the colors, is where INGENUITY is right now. And INGENUITY also, after conjunction, which was a very big milestone, because it was a technology demonstration, and for it to survive for so long is really quite a feat. And so it is also healthy and doing well. And the number of samples, as I mentioned, we cached is 3. So this kind of gives an overview snapshot of the mission. But going back to what we've done in these last 7 months, so Perseverance landed on February 18th of 2021, as many of you are probably familiar. And a location we've headed to is Jezero Crater. And the reason is because it's an ancient river delta, and the chances that it preserves signs of ancient life are very high. And that's, me at the middle left, holding my lucky peanuts, because if you're doing robotic operations, there's a few things, that are important, but in general, sort of our entry, descent, landing team is really taking us down there. And as you can see, we're very excited. And this picture in the middle is a picture, for the first time we had pictures during entry, descent, and landing taken by the cameras. And it was really exciting. This was one of the first images. We, of course, saw the HASCAM before that. For us to see, the mobility system had deployed, everything looked great. And to actually see the rover in the process of landing, because we actually, during the last phase of the EDL, deployed the suspension, and the rover lands on its wheels. And on the bottom right, I just wanted to give it, this is an artist's conception, but it gives you a sense of the scale of the delta. There's the rover there, and you can see it's a very large formation, even though when we are looking at the orbital images, sometimes you can miss the scale of these things. Here is a graph that shows all of the sols in which we have conducted Perseverance robotic operations. And so right from sol 0, we started doing operations, and we really interleave them. Even though we've had 13 flights, we actually communicate with the helicopter a lot. We transfer data, we do other health checks, so there's a lot of communication. And the mobility really is science-driven. Do we want to get to the next target? Do we want to bump a little bit more because we see something interesting just past where we are at? And so it's driven a lot by that. Of course, as we start driving to the delta, that becomes the primary motivator, and it's driven by mobility to try to get to a particular location. And then the robotic arm we deployed quite frequently to do various observations. Some of them are planned. We're trying to get to a specific spot that the science team has been thinking about for a really long time. They've looked at it with distant measurements, with remote science, and we're driving up to it. And some of them are just opportunistic. We happen to see in the workspace image, we always take at the end of a drive something really interesting, and so we deploy the arm and took a measurement on it. And then the sampling, again, covers the brazen GDRT. And of course, this is all covering a lot of what we've done in this mission is also checkouts so far. So this phase in the early part of the mission is a lot of commissioning as well. So in terms of how we command the rover, just Mars, it looks so much like Earth, so familiar, but it's really, really quite far away. And it can take, depending on the relative position of Earth and Mars, it can take up to 24 minutes just for a one-way lifetime signal to get to Mars. And if we were, as we're commanding, if we send them through the deep space network to the rover, we directly command the rover and it receives the commands through the high gain antenna. If you were to send that, and then the rover takes a lot of data and images and transmits it to orbiters around Mars, and then we get that back through the deep space network. If you did that one step at a time, it would be quite slow. So we don't actually command the rover that way, as most of you know. We actually send the entire SOL's activities, and this could be one or more SOLs, to the rover. But the missions we do are really discovery driven. We're really interested in science input. So as we're making discoveries, the more frequently the scientists can interact with it, the more they can update it. Of course, if you're just driving, that doesn't change as much and you want to optimize it. So that's some of how we do our operations. This shows the commands we have sent to the spacecraft every sol. So as you can see, we're sending hundreds of commands. And in the case of sampling, over 1,000 commands to the spacecraft in order to do the operations. Now, this is showing spacecraft commands. Our sampling operations have a lot of abstraction, and we have configurable scripts that do the low level commands. I'm not showing that, so it would be even a lot more commands. You can just see the magnitude of the commanding depending on what we're doing. So it leads robotic operations really very well to autonomy, because when you're operating autonomously, the spacecraft can make some of its own decisions, and also to abstraction. So here I'm just showing an example of one of the tools. We use dozens of different tools to look at the data in different ways and to make the decisions, so we are sort of cognizant of what is available. Now, not everything we want is available at all times, because we have different bandwidth from Mars. Depends on, sometimes we get a lot of data, and sometimes limited data depending on the orbiter passes. Here is an example of how we plan one of our AutoNav drives, which is autonomous navigations. And we do it in this abstract way. We're sketching the drives. There are things that autonomous navigation with the cameras on board doesn't detect very well, such as sand. And you've seen those red geometric zones we draw, which just said, keep away from this, and various other very abstract commanding that we do. And this translates to those commands. So when we're operating, we're not actually thinking about hundreds of commands on a daily basis, but we have the ability strategically to change them, because we've been on Mars for so long, decades, and we've seen that Mars will surprise you. We've been in so many different areas, and yet we continuously find new things we hadn't encountered before. And you want to have that configurability to be able to change things as needed. but you don't want to think about it on a daily basis. So we do that a lot. And this is the surface transition. So when we landed, you'll see, some of the operations we did right away. The top left is showing the first robotic arm unstow, which was actually the first robotic activity, which was an unstow. And I was fortunate enough to be on that day. And, you're seeing just the arm unstowing, but there's a lot going on in the background, like some of the software that I've been involved with writing, like doing collisions, there were hundreds of those being done. So a lot of things are being checked out. We test very thoroughly, but Mars is a third of the gravity. And there are things we just don't test as accurately. We have really good simulations and models, but the first time is very important. And the middle, you're seeing us, checking out our steering wheel, because we land on our wheels. We want to make sure the mobility system works. In fact, we check all of our actuators. We have, 34 actuators on the vehicle, which are just controlled by the rover's motor control assembly. There are additional actuators on the instruments, such as covers. And in fact, Pixel has a hexapod, because when you position it with the surface overnight, the arm can contract because it's so massive, and it can automatically track the surface to make sure it stays on the target it's observing. And then on the right top, you're seeing the very first drive we did. This was a very important moment because it meant that, we actually have a rover that can move from place to place. And you see at the bottom left, there are some one-time deployments we do. One is the mast. So we deploy the mast right after we land so we can start taking images. And here you're seeing us, the belly pan was covered with protecting the sample caching mechanism. So we deployed it, then we drove a short distance. And the helicopter Ingenuity was also covered with a debris shield. And we deployed that. And here you're seeing Ingenuity sideways trapped under the rover. And all of these images, the ones that you're seeing under the rover, are taken by taking the robotic arm, positioning the Watson camera under the rover, and taking this imagery. So whenever you look at an image, I always think about, like, how did we take this image? And that's often interesting operations in itself. In the bottom middle, you're seeing us touching the surface for the first time. And you're also seeing the images of the Watson camera where we do refinements, where we iteratively get closer. And we actually use the Watson camera's focus mechanism to tell us more accurately than the robotic arm positioning certainty, how close the surface is if we can't touch it. Touching it, of course, gives us a lot of accuracy. And then on the bottom right, you're seeing us, opening the bit carousel door and starting to really check out the sampling mechanism. And then, this mission was special in a way because we had a second robotic spacecraft along, which was the Mars helicopter. It's a technology demonstration. And it was a 30-day technology demonstration to demonstrate the first powered flight. So right as we landed, we knew where we were. Right away, we started looking for where the most interesting airfield would be to deploy the helicopter. There were some requirements. It had to be flat. It had to be, have very few hazards. And we had certain very precisely defined criteria for that. And also have enough features so that the helicopter's navigation cameras can actually track them. We also had imagery from the rover. So we started looking at areas that were very close. We also looked at a site that was further along. But if the site closer worked, we would have much more detailed information from the rover's own imagery. And as it happened, slowly as we were working through all the criteria, we had, a lot of meetings. We were analyzing a lot of this data, realized that the site does meet the requirements. And what was then left was to figure out precisely where we wanted to position the airfield and then, rotate the whole flight zone around it. And then another important aspect was the rover was going to observe these flights. All of the images and video you see of Ingenuity flying were taken by the rover. And that's another really interesting operational challenge because, the flights in the beginning, they're on the order of a minute to 90 seconds max. And you're trying to time that very precisely with all the uncertainty that comes from robotic mechanisms with a camera and also, the frame rate, and you're trying to optimize the rate at which it's collecting data around the most important part of these flights. And this is another image showing this drive that we were doing. We did multiple drives. We approached it from the south, and you're seeing a drive as we're skirting along, coming down towards it. And this is on the right, you're seeing imagery we had taken. So when we went off to deploy the debris shield and we were doing some of the checkouts, we actually drove past the airfield because we already knew it had high potential, to take close-up imagery so we could actually really carefully analyze all of the rocks in that area. And this is another one of our tools showing in the image as we're driving up. And we can actually visualize all of these tools, although we have a lot of different ones, they all combined into a common framework. And you can, visualize the helicopter and the rover. And at the moment, of course, as we were driving, the helicopter was strapped under the rover. We hadn't deployed it, but we could visualize what it would be like once we deployed it. And this is a picture. It was a very exciting day when you're seeing, we've actually gone through on the left multiple steps of deploying Ingenuity, because we release one leg at a time, and here it is in the last stage where all of the legs have been deployed, but it's still attached to the rover and just hanging off, centimeters from the surface. And this was a very important drive, because we were going to deploy the helicopter. Once you fire the French bolt to deploy Ingenuity, it's no longer attached to the rover, which means it was no longer going to be able to charge from the rover. And the sonar panel had to be unshaded. And that had to happen within 25 hours. Otherwise, the Ingenuity mission was at risk. So it was a very important drive. And we went through a lot of checks to make sure that we minimized the complexity of it. So we weren't doing anything unnecessary. At the same time, took away actually some of the safety checks so we wouldn't get false triggers. But at the same time, Perseverance is a Class B mission, which has a categorization of how important it is as a national asset and the science it returns. And Ingenuity was a Class D mission. So we made sure that the rover was always going to be safe at all times, and but maximize the chance that Ingenuity would survive and get to do its first flight. We also had an additional link where after the French bolt had fired, we didn't have enough bandwidth to Mars that we could actually send another plan in case that hadn't worked. But we had what we call a direct to Earth link, where we would be able to get some small amount of telemetry. So we could tell, based on our analysis, if the autonomous detection on board had been accurate. And if not, we could actually deactivate the drive sequence. And we had one more chance the next morning to drive off. So there were a lot of things we put in place that you have to think about when you're trying to coordinate two missions. And that is the image on the right showing it was a very exciting day, seeing us having succeeded the drive and Ingenuity having been deployed. And then this is an image of the first self-portrait we took, where Perseverance took this image with the helicopter. And this is a really neat image, because nominally in the mission, after the deployment, Ingenuity was going to drive, Perseverance was going to drive off, and we would never again nominally be so close to the helicopter again. And this was a development, done at a very quick clip, and it's very actually much more difficult to take a self-portrait on the Perseverance rover, because the turret is so large and the bit carousel is there. There's actually a lot more probability of colliding with the rover's body. You don't see the arm in the image, which is what is taking this entire selfie. It's composed of 62 frames taken by the Watson camera. And that was, again, operating that. It takes 1 hour of robotic arm motion. And here I'm just showing stills we took. So while we were taking the Watson image, we actually also commanded in parallel to take images from the mast, looking at the Watson camera, taking the selfie images, so that we could create this frame of seeing, the arm moving for this process. And towards the end of this movie, you'll see the Watson camera's cover close. And these, this is composed of a little over 150 frames. So it's just stills. And so that's why you don't see a continuous arm motion, but you can see some more details on the details of what it takes to actually compose this image and all of the arm motion involved in creating the image you saw on the previous page. And then here, prime part of the mission really is the science. We're there to study the geology, the astrobiology, and find signs of ancient life, which we're doing by caching these sample tubes. And then, also prepare for humans. And there you're seeing, the sample cubes at the Space Center, or Kennedy Space Center before launch, with very stringent cleanliness requirements being installed. And then once we've done the flights, and I haven't gone into, because I know Teddy talked to and went into all the details of all of the flights and all that we were able to do with that is to really get to the delta, to accomplish the rest of the science mission. And here we're starting to look at some notional paths going counterclockwise and clockwise to get to the delta. And for this, what's really very valuable is autonomous navigation, because we want to cover distance, and we can only see a certain, distance from the horizon, because there's occlusions and there's a view shed. We do a lot of autonomous driving, and autonomous driving really allows us to cover a significant amount of distance. And here I'm showing an image of a checkout of the autonomous capability where you're seeing it swerve around that obstacle. And these images on the bottom are showing the left and right camera images of the actual images that AutoNav used to take a picture of the terrain, analyze what the hazards were, and find a path in it. Perseverance autonomous navigation also has to think about, when we're driving, you also have to think about other factors, such as a helicopter. And here you look at a drive where we are driving right past INGENUITY, and we want to keep a safe distance as we are even autonomously driving, so that we put a keep out zone around it. Although the hazard detection could detect it, we want to maximize that the rover doesn't get close to it. The Perseverance AutoNav is almost 10 times faster than Curiosity. We actually have a dedicated processor on board. It's also a RAD 750 because there are requirements for the robustness and reliability. But it is a dedicated processor that does the stereo processing, and so it can do. And we also have an FPGA that does the stereo image processing. We could do it so fast that as the wheels are turning, we call it thinking while driving, that we can do the image processing, think about whether the terrain is hazardous while we're still turning the wheel. So it really doesn't slow us down. And I'm going to show this next graph, which shows the amount of driving we've done. And there's different modes, but shows you how much we've driven autonomously so early in the mission, which is a lot more. There is a certain amount of driving in the beginning before the AutoNav capability was deployed, where we're doing these directed drives. We always use visual odometry because there's so much slip and sand on Mars that helps us tell where our position is. We use it in conjunction with AutoNav. And there are certain times when we were characterizing whether certain sandy terrain, how AutoNav was performed, because this area of Mars is very new, and we use what we call guarded mode, where we're actually driving based on the direction from ground, but we're actually seeing how AutoNav would have driven. So you can see we're doing a lot of autonomous driving. And it's been very important. This is showing CITADEL, which is the location that was very interesting to science. But where we were, we couldn't see that far because we were actually downslope from it in SETA region. And we were also going to have to cross the ridge in a gap, and we would certainly not be able to do that in the time in one drive. But we also wanted to try to do all of this before conjunction, so we would have the data to analyze on Earth. And here you're seeing this drive where we were able to drive along and then turn on AutoNav, and with visual odometry and AutoNav, we were able to make it through that pass and get all of the distance with AutoNav. So it really allows us to do things like this. And here, just a little bit past that ridge, we found a really interesting target, which ended up being the Rochette. And we drilled 2 sample cores and cached them. And this is, again, another location at which we took the selfie. Typically, once we've taken the first selfie, we execute exactly the same command. So the second one is a lot easier because it's much the same commanding. We change the imaging of how we're pointing the mass so that it's looking at, in this case, the helicopter was in close by, we were looking instead at the drill holes. And when we do the sampling, there was a lot of in-situ observations that go along with that. Here you're seeing the arm deployed to take imagery. We create an abraded patch, and on the top right, you're seeing pixel instrument and the results that we got from analyzing that abraded patch, and after we had blown away dust from it. But after we drill, very quickly things get filled in with dust after we clear them out. And then with the Sherlock instrument, all of those dots show all of the locations in which we took Sherlock observations. And that actually is a picture of the Rubicon drill hole, but again, we image the drill hole after we take it. And in the middle bottom is a picture which is really very exciting, because that is a cache cam. That's a camera inside the rover's body that shows us sealing the sample tube. And here on the bottom left, you're seeing the actual sample core. So that is very exciting because it starts us off on really this first leg of the proposed, the planned sample return mission, where we're going to be at some point launching these samples from the surface of Mars to bring them back to Earth. And they can be studied in all of the laboratories that we have available on Earth. And this image here is the image taken from the Mars Reconnaissance Orbiter. And it shows Perseverance where it is in South Zeta. And you can see, the tracks. I love these images from orbit. You can actually see the tracks of the rover and see all of the locations we were at. So that's where we were at. And we're going to continue on to collect a few more samples before we start on the long drive and do a lot of autonomous driving as we drive along to get to the Delta. So yeah, at this point, if there are any questions, I'd be happy to take questions.
Thank you, Dr. Verma. And there are questions, of course. So let's start with the first one from Dusty. They say, how do you think AI and things like Tesla, FSD, and Dojo will affect the future of robots on Mars?
Actually, it already is. So we actually have a lot of artificial intelligence capability on board Perseverance as well. Some of it we haven't quite used as yet because, we deploy them in stages. But for example, Perseverance, can take an image, and this is some of it which I worked on Curiosity, and we're bringing to Perseverance. We could take a wide-angle camera image. In that, as we're driving along, we might miss things, but when it takes the picture, it can look at what's interesting in it based on what scientists on Earth defined as being interesting. And you could change that criteria. You can say, well, I'm interested in rocks of a certain size and shape, of a certain albedo, and it will then find the most interesting such rock, prioritize it, and can point the narrow angle instruments such as the RMI imager and actually zap it with the laser and send the data back to Earth without requiring ground to have saying, hey, I saw an interesting thing, take a measurement. So we do have that capability. We also have capability planned that we'll be putting on board, where we are going to be doing onboard planning, where the rover will be taking some measurements and decide, well, actually, it took a lot less energy because we keep margin on to do things. There's extra time. I might add in some opportunistic measurements because that's interesting. Or if something fails to happen, it might then put in other constraints and put in other activities. So there's a lot of that happening. And I think that really is very important, especially for Mars, because as we go even further out beyond Mars, the communications delays are so much that what you can do on board without ground in the loop, because the rover knows more once it started driving, you don't know what it's going to see. That's really going to help with the science return.
Thanks for the answer. Next question is from Nicholas. How long might both missions last? And have you already found problems with the missions that will inform designing the next generation rover?
You're right. These are great questions. So the mission, the nominal time is, 1 Martian year. So that's approximately 2 Earth years in which it's going to, cache and collect these sample cores. And for Ingenuity, really, it's in overtime already, because Ingenuity was supposed to last 30 days, and here we are, over 200 cells into the mission. How long it'll last? The first rover I drove on Mars was the Opportunity rover, and a lot of us would say, you stop betting against these rovers beyond a certain point. And I would love to see Ingenuity come all the way with us to the Delta, following along with the rover and scouting. So, I think if past missions are any sign, it could be a long time, but I will let the rovers decide.
Wonderful.
And actually, the second part of the question, sorry, I forgot about that, whether we've seen issues. It's been kind of really interesting. Of course, we see issues right after launch. There are some interesting characteristics because there's so much going on in parallel. There'll always be some things that are intriguing. They may not cross the bar into being an anomaly, but we have seen things, right? Ingenuity, we've seen this watchdog timer issue, and we updated the software so as not to hit it. We see, other issues with different aspects of it. And every time we see an issue, it absolutely informs the subsequent mission to say, is there something we could do to minimize it? At times you can eliminate it. There are other times where you can do your best to minimize it. And you wonder, we have processes in place. How did this happen? That is a huge aspect of what we think of almost immediately after we encounter the situation. So yeah, with Ingenuity, with the watchdog timer issue, it was interesting because we didn't see it in our test rover on Earth. We only saw it on Mars. And so that's another characteristic of saying, what is the difference between the two and how do you ensure that you can replicate these? But there will always be certain differences between the flight vehicle and the test, even when you build full-scale replicas. And that we always try to, that we will always just see based on statistics, if it's something that happens once in a while, such is the case with a lot of race conditions and other probabilities. That's why we do a lot of regression testing as well to eliminate those. But all of these inform the subsequent mission. In fact, Perseverance has benefited a lot from the lessons we learned from the Mir rovers, from Curiosity, and even going back to Sojourner.
Thank you so much, Dr. Verma. There are, again, a lot of questions and comments, but unfortunately we are running out of time. So again, if you do have a little bit of time to answer them via the Q&A panel, via chat, that would be amazing. Otherwise, thank you so much for your time. It was very insightful.
Great, thank you so much. Bye-bye.